11.3. Angular momentum of a rotating rigid object. The outline of this video is as follows. We will begin by deriving the rotational form of Newton's second law, which relates the net external torque on a system to the rate of change of its angular momentum. Next, we will discuss the specific conditions required for the angular momentum vector, L, to be expressed as the simple product of the moment of inertia, I, and the angular velocity vector, omega. After covering these theoretical points, we will test our understanding with a short conceptual quiz. Finally, we will apply these principles to a detailed worked example involving a father and daughter on a seesaw to see how these concepts work in a real-world scenario. To determine the total angular momentum of a rotating rigid object, we can begin by analyzing the contribution from a single, representative particle within it. Let us consider an object rotating with a constant angular speed, omega, about a fixed z-axis. A particle of mass, m sub I, is located at a radius r sub I from this axis. Its tangential velocity, v sub I, is equal to its radius r sub I times the angular speed omega. The magnitude of this single particle's angular momentum, L sub I, is its mass times its velocity times its radius. If we substitute the expression for velocity into this equation, we get L sub I equals m sub I times the quantity r sub I times omega, all multiplied by r sub I. This simplifies to the expression L sub I equals m sub I times r sub I squared, all times omega. Importantly, for this case of rotation about the z-axis, the angular momentum vector for the particle points along the z-axis, this direction is parallel to the angular velocity vector, omega. The key result is that each particle's contribution to the total angular momentum is proportional to the square of its distance from the axis of rotation. Now we will combine the results for individual particles to find the total angular momentum of the entire rigid object. This process will lead us to a very important and compact equation. First, we find the total angular momentum along the z-axis, which we call Lz, by summing up the individual contributions from every particle in the object. This gives us a summation of the quantity, mi times ri squared times omega. A key feature of a rigid object is that every particle rotates with the exact same angular velocity, omega. Because omega is a constant for all particles, we can factor it out of the summation. The expression that remains inside the sum is the sum of mi times ri squared over all particles. You should recognize this from our study of rotation as the object's moment of inertia, I, about the axis of rotation. This simplifies our expression beautifully, giving us the central equation for the angular momentum of a rigid body, Lz equals I times omega. Notice how this is a perfect rotational analog to the equation for linear momentum, which is P equals m times v. We can now derive the rotational equivalent of Newton's second law, which connects the net torque on an object to its resulting angular acceleration. The derivation begins with the general principle that the net external torque equals the time rate of change of angular momentum. For a rigid object, we can substitute our expression for angular momentum, which is the moment of inertia I times the angular velocity omega. Since the object is rigid, its moment of inertia is constant with respect to time, so we can pull I outside the derivative. This leaves us with multiplied by the time derivative of angular velocity. By definition, the rate of change of angular velocity is the angular acceleration, alpha. This brings us to the final, crucial equation. The net external torque equals the moment of inertia times the angular acceleration. This relationship, tau equals I times alpha, is the rotational analog of F equals m times a. and it forms the foundation for analyzing the dynamics of rotating rigid objects. Let us now consider the full vector nature of angular momentum. Under specific, ideal conditions, we can write a simple vector equation. The vector L equals I times the vector omega. This special case applies when a symmetrical object, like a spinning disk or sphere, rotates about an axis that passes through its center of mass. In this situation, the total angular momentum vector L points in exactly the same direction as the angular velocity vector omega. However, it is very important to know that this simple vector relationship is not always valid. If an object is not symmetrical, or if it rotates about an arbitrary axis, the angular momentum and angular velocity vectors may point in different directions. Describing this more general case requires treating the moment of inertia as a more complex quantity called a tensor. The good news is that the component form we have been using, L sub z equals I times omega, is always valid for the component of angular momentum along the axis of rotation. So remember that the simple vector equation is a special case, but the component equation is a reliable and general tool. Let us work through this question, which asks us to compare the angular momentum of a solid sphere and a hollow sphere. The key relationship is that angular momentum, L, equals the moment of inertia, I, multiplied by the angular speed, omega. The problem states that both spheres have the same mass, the same radius, and rotate with the same angular speed. Since omega is the same for both objects, the one with the larger moment of inertia will have the higher angular momentums. So the question really comes down to which shape has a larger moment of inertia. Remember that moment of inertia depends on how an object's mass is distributed. For a hollow sphere, its mass is concentrated farther from the axis of rotation compared to a solid sphere of the same mass and radius. The formula for a hollow sphere's moment of inertia is 2/3 mr squared, while for a solid sphere it is 2/5 mr squared. Since the fraction 2/3 is greater than 2/5, the hollow sphere has the larger moment of inertia. Therefore, the correct answer is that the hollow sphere has the higher angular momentum. Let us begin by calculating the angular momentum for this father-daughter seesaw system. The first and most important step is to find the system's total moment of inertia, which is its resistance to rotational motions. Because this system is made of 3 distinct parts, we can find the total moment of inertia by simply adding the individual moments of inertia for each part: the rod, the father, and the daughter. For the seesaw rod rotating about its center, the formula is 1/12 times its mass, m, times its length, L squared. We model the father and daughter as particles, so their moments of inertia are each given by their mass times their distance from the pivot squared. Since they are at the ends, their distance is L/2. So we add m sub f times the quantity L/2 squared and m sub d times the quantity L/2 squared. Summing these 3 terms and simplifying gives the total moment of inertia, I. Once we have this value, the magnitude of the angular momentum, L, is simply the total moment of inertia multiplied by the angular speed, omega. Now, let us find the angular acceleration of the seesaw at a given angle. Our strategy is to calculate the net torque on the system and then apply the rotational version of Newton's second law, which states that net torque equals moment of inertia times angular accelerations. The net torque is produced by the gravitational forces on the father and the daughter. The board's own weight and the upward force from the pivot both act at the axis of rotation. Because their lever arm is 0, they contribute no torque to the system. The torque from each person is their distance from the pivot, which is LL/2, multiplied by the component of their weight that is perpendicular to the seesaw. This component is m times g times the cosine of theta. By convention, the father's weight causes a counterclockwise or positive, torque, while the daughter's weight causes a clockwise, or negative, torque. Summing these gives the net torque, which is proportional to the difference between the father's mass and the daughter's mass. To get the angular acceleration, alpha, we simply divide this net torque by the total moment of inertia, I, which we found in the first part of the problem. Let us now consider two what-if scenarios to deepen our understanding of this system. First, what happens if the father moves inward from the end of the seesaw to a new distance, d, from the pivot? This change affects two key quantities. It reduces his lever arm, which alters the net torque on the system. It also brings his mass closer to the axis of rotation, which reduces the total moment of inertia. The new angular acceleration, which we can call alpha prime, is simply the ratio of this new torque to the new moment of inertia. Our second scenario asks a practical question. Where must the father sit to perfectly balance the seesaw? In physics, a system is balanced when its angular acceleration is 0. For this to happen, the net torque must also be 0. We can find this special position by taking our expression for net torque and setting it equal to 0. Solving that equation for the distance d shows that the balance point depends on the ratio of the masses. This result confirms our intuition. The heavier the father is compared to his daughter, the closer he must sit to the pivot to balance her. Let us summarize the two fundamental equations that describe the motion of a rotating, rigid object. First, for an object rotating about a fixed axis, its angular momentum along that axis, L sub z, is the product of its moment of inertia, I, and its angular velocity, omega. This relationship, L sub z equals I times omega, is the direct rotational analog to linear momentum, where P equals m times v. The second key equation is Newton's second law for rotation. It states that the net external torque, tau, acting on the object is equal to its moment of inertia, I, multiplied by its angular acceleration, alpha. This is the foundation for analyzing rotational dynamics. Finally, it is crucial to remember a specific conditions. The simpler vector relationship, where the vector L equals I times the vector omega, is only valid when a symmetrical object rotates about an axis of symmetry that passes through its center of mass. For more complex rotations, the angular momentum and angular velocity vectors do not necessarily point in the same direction. Let us wrap up with a couple of questions to test your understanding of angular momentum and torque. The first question asks you to compare a solid disk and a hoop. They have the same mass, radius, and angular momentum. Your task is to figure out which one has a larger angular speed. To solve this, start with the fundamental relationship between angular momentum, moment of inertia, and angular speed. Think carefully about how mass distribution affects the moment of inertia for these two different shapes. The second question takes us back to our seesaw example. We calculated the net torque using only the gravitational forces on the father and daughter, but other forces are acting on the system, such as gravity on the seesaw itself and the support force from the pivot. Why did we ignore these in our torque calculation? The key here is to remember the definition of torque. Consider the point of application for each force and its distance from the axis of rotation. Take a moment to pause and think through these problems. Working them out is an excellent way to make sure you have mastered these concepts.